All right, let's go ahead and get started. I do want to welcome you back to Unit 7. This is Chemical Reactions, and we have been talking about radioactivity. Now, we want to focus now on something called radioactive half-life. What do we mean by radioactive half-life? Well, an isotope which is radioactive is in a state of constant decay. It's spewing material, particles, and/or energy from the nucleus. The amount of time that it takes for half of the radioactive material to go away is called half-life. All right, half-life. So let's take a look at this graph that shows radioactive decay. So if we look on the x-axis, this is time in years, and on the y-axis, this is mass in grams. If we start with 10 grams of material, this is a radioactive material, strontium-90 that we're looking at, and we start with 10 grams of it, the question that we have is, how long does it take for half of the material to disappear? So in other words, how long does it take for us to get to the 5-gram mark? The answer is, if we move across, 25 years. So the half-life for this material is 25 years. If we wait another 25 years, half again is going to be gone. So we're going to go from, say, 5 to about 2.5, right about there, just like that. And if we go down again, we have another half-life and so forth. So the point of all this is that a half-life is the time required for half of the initial material to disappear. Half of the radioactive material to disappear. So strontium-90 then is a radioactive isotope. The half-life for this isotope is about actually 27 years, right? So it's a little bit longer than 25 years. So if you begin at time 0 with 10 grams of strontium-90, you end up with only 5 grams at the end of the first 27 years. After 54 years, or 27 times 2 years, you're left with half of that, half 5 grams, or 2.5 grams, and so on. So scientists use this property of radioactivity of materials, or radioactive materials, to do things such as radioactive dating of very old things. So sometimes maybe a scientist will find something in the field and want to know how old it is. They can use this procedure. So that's radioactive dating and radioactive decay in a nutshell. And that's all I'm going to say about that for now. We're probably going to have a whole unit on radioactivity later on in the year, but for right now, I just wanted to introduce that topic. And we're going to finish up chemical reactions with something called reaction equilibrium. All right, what do we mean by equilibrium? Well, as it turns out, reactions don't go in just one direction. For the most part, reactions are reversible, meaning that they go from reactant to product and from product back to reactant. Okay, most reactions are reversible, meaning that the reaction is in a state of constant change, moving back and forth, moving in the forward and reverse direction simultaneously. All right, at the same time. This is known as equilibrium. So equilibrium then, in the following balanced reaction, ammonia reacts with iodine to form nitrogen iodide and hydrogen gas. All right, so this is the reaction here. We have ammonia plus iodine yields nitrogen iodide and hydrogen gas. Now notice the double-headed arrow, the arrow going back and forth. So what that tells us is that when 2 parts of ammonia are reacted with 3 parts of iodine, it forms 3 parts of nitrogen iodide and 3 parts of hydrogen gas. But just as quickly, it goes back the other way. So it's in this equilibrium going back and forth. Let's think of an analogy. Let's say, for example, let's think of SeaWorld, all right? At SeaWorld, during the day, there is an equilibrium of people going into the park and coming out of the park. In other words, if you were to pick a time, let's say 3 o'clock in the afternoon, on a July afternoon, right? People are going in and people are coming out of the park. It's not like everybody's going in or everybody's coming out. Simultaneously, there are some people that are going in and there are some people coming out. Well, that's kind of like equilibrium. All right, that's kind of like equilibrium. Now, here's what we know about equilibrium. First, the concentration of each chemical in the reaction remains constant over time. All right, so that's the important thing, that over time, when you have a true equilibrium, that the concentration of each chemical is constant. That's critical. Second, the rate of the forward reaction and the rate of the backward reaction are the same. Forward reaction, backward reaction are equal. And the third thing is the system is closed. In other words, no other chemicals are involved in this reaction. And finally, the value which describes precisely where the equilibrium lies is known as something called the KEQ. And this number, this KEQ, is temperature dependent. In other words, if you change the temperature, the KEQ changes. This number which describes the equilibrium is going to change. All right. So let's talk a little bit then about this KEQ, also known as the equilibrium constant or the expression law for equilibrium. The KEQ is equal to the product of each product. Sounds redundant, but it's supposed to be that. Product meaning multiplication, and this product right here, I mean multiplication, and here I mean the things on the right side of the arrow. So the KEQ is equal to the product of each product raised to the coefficient in front of it in the balanced reaction divided by the product of each of the reactants raised to each coefficient. So for this reaction, let's scroll back up. I don't think I can have them both on the same screen at the same time, but we have 2NH3 plus 3I2 yields 2Ni3 solid over 3H2. So we're going to remember this part first. We have 2Ni3 plus 3H2. Those are going to go in the numerator, the top part. So here we go. Ni3, nitrogen iodide, had a coefficient of 2. Notice the coefficient becomes a superscript times, this is a product now, the other product, which is H2, to its coefficient, which was a 3 in the balanced reaction, right? So which was a 3 in the balanced reaction. So let's just check that. 2 parts of Ni3 plus 3 parts of H2. So these coefficients become products in the KEQ expression. They become products in the KEQ expression. Now on the bottom side, we have on the denominator, we've got the reactants. In this case, we have NH3, ammonia to the second power. Since this was a coefficient, since this was a coefficient, it becomes a superscript times, it's a product, I2. Whoops, make this 2 down here. Let's take that down. I2 to the third power, just like that. I2 to the third power, just like that. And that then is the KEQ expression. So it tells us the relationship between products and reactants for that expression. So it's going to be some number, right? Now that number, we've already said, is temperature dependent. In other words, if you change the temperature, you change the KEQ because the concentrations are going to change, right? What's in here is going to change. So KEQ, again, is temperature dependent. Now, a KEQ of less than 1 implies that the equilibrium lies more to the left, obviously because of the fact that there's less reactants, there's less products than reactants, right? But a KEQ of more than 1 implies that the equilibrium lies to the right. All right? So that's equilibrium. Now what I want to talk about in the last section of these notes is something called Le Chatelier's principle. Okay? Le Chatelier's principle says this. It states, essentially, that the reactions in equilibrium will resist changes to the equilibrium state. What does that mean? If a reactant, for example, is removed, the reaction will move to the left. In other words, Le Chatelier's principle says that it's going to counter whatever action you have, that the equilibrium will be maintained even if you change something in the equilibrium expression. If a product is removed, the reaction will move to the right. And for a reaction which is exothermic, heat is produced is a product. So if the reaction is heated, the reaction equilibrium moves to the left, away from that side. So let's take a look at these specific examples and see if we can determine, we'll go the other way, what exactly Le Chatelier's principle means. So let's look again at that reaction. So the reaction was this. The reaction was 2 parts ammonia plus 3 parts I2 in equilibrium with 2 parts Ni3 plus 3 parts H2, right? And the equilibrium goes back and forth just like that. Now, what Le Chatelier's principle says is this. if you attempt to disturb, if you try to change anything in this equilibrium, that the equilibrium itself will change in such a way, it will shift in the direction of the change that you made. So for example, let's just say that you decide to add more NH3, okay? You put more NH3 in here. So I'm going to say plus more ammonia, more NH3. What's going to happen is that the equilibrium is going to say, listen, everything was just the way I wanted it. Why did you do that? Why did you add more ammonia? I didn't want you to do that. I'm going to get rid of that ammonia that you put in by shifting more to the left, to the right, away from where ammonia is, right? Now, there's still going to be movement to the left, but it's going to be outweighed by the movement to the right because of the fact that you've disturbed the equilibrium. This is called a perturbation of equilibrium. So by changing the amount of NH3, you shifted the equation to the right. Okay? So let me erase that and let's take another scenario. Let's say, for example, that we were to say, you know what? Here's what we're going to do. We're not going to put more NH3 in. We're going to take some NH3 out. We're going to remove ammonia. What the equilibrium is going to do is going to say, why did you do that? I was comfortable with the amount of ammonia that I had, and now you're taking it away. But you know what? I'm going to counterbalance what you did. If you took ammonia away, I'm going to shift this equilibrium further this way in order to reestablish the amount of ammonia that was there to begin with. Does that mean there's no movement to the right? No, there's still movement to the right. It's just not as much as there was. The shift is going to occur to counteract what you did, all right? What you did. And the same can be said about any of these chemicals here. Now, we talked about exothermic reactions and endothermic reactions and how Lachat liaised principle is involved here. Let's just say that we have an exothermic reaction. If we have an exothermic reaction, we can think of heat as being on this side of the reaction, right? We can think of heat as being over here. So what happens if I have a KEQ? In other words, I have an equilibrium, but then I heat up the reaction. I heat up the reaction, okay? Lachat liaised principle says that heat is just like any of the other products, the Ni3 or the H2. If you heat up the reaction, it's going to say, why did you do that? I had the amount of heat that I wanted, and now you messed it up. So if you add heat to the heat that was already present, right? What's going to happen, by the way, you can't you cannot add heat to the right side or to the left side. I put it on that side just to compare it to this heat right here. The point is that what the reaction is going to do, what the equilibrium is going to do, is going to shift away from where the heat is, right? Shift away from where the heat is. There will still be equilibrium reaction in the opposite direction, but the equilibrium will shift because you added heat, all right? Now, what happens if you do this? Let's erase this, and let's now cool it down. Now, let's just say this time, though, it is an endothermic reaction. If it's endothermic, that means that energy, you know what? Let me do this. Let me make this heat. I was going to write energy, but let me write heat, okay? So heat added, or I'm sorry, heat on this side, right? It requires heat to make the reaction go. It's endothermic, right? Endothermic. So what's going to happen if you cool the reaction down, right? What's going to happen if you cool the reaction down? Well, what's going to happen is that if you cool the reaction down, it's going to say, why did you do that? I need to go where there's more heat. You cooled it down, so the reaction is going to shift this way, all right? You're still going to have some movement this way, but it's going to be mainly to the left because you cooled it down and it was an endothermic reaction. Folks, that is Lachat liaised principle. That will do it for this unit. I'll see you in the next one. Thanks.